Okay guys, in this video we're going to be talking about the effect of temperature on reaction rates and what's known as the Arrhenius equation. So we were first introduced to the rate constant back when we talked about rate laws or differential rate laws, right? And at that time we said that K was a constant, and it is, but it's only a constant when the temperature doesn't change. K actually depends on temperature, so mathematically the way we incorporate the temperature dependence of reaction rates is through the temperature dependence of the rate constant. And the temperature dependence of the rate constant is given by the Arrhenius equation. And so here's K, the rate constant we've been dealing with. A is called the frequency factor. EA is the activation energy. R is the gas constant. And so we've encountered this a couple times already. We encountered it when we did the chapter on gases, and we encountered it again when we talked about enthalpy. The form of the gas constant that we want to use in these examples is that R is 8.314 joules per mole times Kelvin. And so this also impacts what the units on the activation energy and the temperature have to be. So the activation energy has to be in units of joules per mole, and then the temperature, T, has to be in Kelvin. And so when you're doing these calculations, if you use the activation energy in joules per mole, in R in joules per mole times Kelvin, and the temperature in Kelvin, then whatever is in the exponent should come out to be unitless. Another note on units, as we've seen before, the units on K can be different depending on what the order of the reaction is, but it will always be the case that the rate constant will always have the same units as the frequency factor. Alright, so what exactly is this EA, the activation energy? Well, in most chemical reactions, there's an energy barrier that separates the energy of the reactants from the energy of the products. And in order for the reaction to happen, the molecules involved in our reaction have to have enough energy to get over that energy barrier, and this energy barrier is what we call the EA, the activation energy. And another important concept related to activation energies is what are called transition states. So over the course of the chemical reaction, we have to break the bonds that exist in our reactants, and we make the new bonds that exist in our products. And so what the molecules look like at the transition state is something in between what the reactants look like and what the products look like. So I don't exactly know what the transition state looks like for this particular reaction, but I do for the reaction that we have on the next slide. So let's go to that next slide and talk more about transition states. All right, so here's the reaction between carbon monoxide and methane. And what essentially happens in this reaction is the carbon from the carbon monoxide essentially inserts itself in between one of the carbon-hydrogen bonds of the methane, right? So here's, what was our CO molecule, right? And so we formed this new carbon-carbon bond, and then we broke one of the carbon-hydrogen bonds, and we made a new bond between the carbon that was part of the carbon monoxide and that hydrogen. And so we can see here, right, this tells us how the energy changes as the reaction progresses. And so at the highest point here, this is where the transition state occurs. And so the transition state is sort of in between what the reactants look like and what the products look like. And so we've started to break this carbon-hydrogen bond. We've started to make this new new carbon-hydrogen bond, right? And we're starting to make this new carbon-carbon bond. But all of this is sort of happening at the same time. And so the transition state really represents the transition separating the reactants from the products. And it occurs at the point of the highest energy, right? So if I was going to label the activation energy on here, that would be the difference between the energy of the transition state and the energy of the reactants. All right, so why do most chemical reactions, in fact, increase in rate? The rate increases as the temperature increases. So back when we talked about gases, we talked about the fact that the energy is a measure of the average kinetic energy of the molecules in our sample. And so this plot on the right here represents the energy that the molecules have and the number of molecules that have that energy. And we have two temperatures. We have T1 represented by the blue curve and T2 represented by the red curve. And T2 is a higher temperature than T1. And so we can see what happens as we increase the temperature, right? The distribution sort of spreads out, but more molecules have higher energy at the higher temperature than they do at the lower temperature. And so if this is the activation energy, the molecules can only react if when they collide, they have as much as the activation energy or more energy than the activation energy. Otherwise, right, they can't get over the hump. They just fall back and return to the reactants. And the chances that when the molecules collide, they'll have enough energy to get over the activation energy. More molecules have that energy at higher temperatures than they do at lower temperatures. So one of the reasons the rates of most reactions increase when we increase the temperature is because when the molecules collide at the higher temperatures, they're more likely to have enough energy to get over the activation energy. Now, the other part of the Arrhenius equation is the frequency factor. And so the frequency factor accounts for how frequently molecules collide, but they also account for the fact that when the molecules collide, they very often have to have the proper orientation in order for the reaction to happen. And so let's see what I mean by that. So let's go back to the reaction between carbon monoxide and methane. Right? In order for this reaction to happen, the carbon end of carbon monoxide has to be the end that collides with the methane. Right? If the oxygen were to hit the methane, we don't want to make an oxygen-carbon bond. We want to make a carbon-carbon bond. And so even if the molecules have enough energy to get over the activation energy, if they don't collide in the proper orientation, then they're still not going to react. And so mathematically, this is accounted for in the frequency factor, or the A in the Arrhenius equation. All right, so I think now is probably a good time to look at some examples of calculations involving the Arrhenius equation. So what I'd recommend, I didn't want this video to be too long, so I actually put the examples in separate videos. So now would be a good time to pause this video and go look at examples 1 and 2 about the Arrhenius equation. And then once you're done with those, come back and watch the end of this video. Okay, hopefully you've had a chance to watch those example videos. What I want to do now is I want to rearrange the Arrhenius equation to write it in a slightly different form that will allow us to do other useful calculations with it. And so I'm going to start with the Arrhenius equation in the form that we've seen already. So we have K is equal to A e to the minus activation energy over RT. And what I'm going to do is I'm going to take the natural log of both sides of this equation. And that may seem random, but I think by the end you'll see why we chose to do this. So on the left I have the natural log of K. On the right I have the natural log of A times E to the minus EA over RT. Now, one property of logarithms is that if I multiply two things inside the logarithm, one of the identities is I can write that as the sum of the logarithm of the first part of the product plus the natural log of the second part of the product. So what that allows me to do is to rewrite that right-hand side. So let me write the left-hand side there. And then the right-hand side becomes the natural log of A plus the natural log of e to the minus EA over RT. All right, and so now the reason we took the natural log of both sides maybe becomes clear. So the natural log and the exponential function are inverses of one another. So when I take the natural log of e to the something, effectively the natural log and the e cancels out, and I'm just left with the argument of the exponential. And so this equation becomes the natural log of k is the natural log of a minus EA over RT. All right, and then I'm just going to rewrite this one more time. I'm just going to swap these two terms. And so we end up with the natural log of k. And I'm going to write that minus EA over R slightly differently. I'm going to write it as minus EA over R times 1 over t plus the natural log of A. All right, now, this may seem random, but now we have the Arrhenius equation in an incredibly useful form. We've written it in the form of a line, right? A line normally has the form y is equal, a straight line, y is equal to mx plus b, right? And so in this new form of the Arrhenius equation, this is my y. The minus EA over r takes the place of the slope. 1 over t is my x, and then I have plus b, where the natural log of a is my y-intercept. And so if I make a plot not of k versus temperature, if I just plot the rate constant versus temperature, I will not get a straight line. However, if I make a plot where y is the natural log of k, and for x I use the inverse of t, 1 over t, if I make that plot, I will get a straight line. And the useful thing about that now is the slope of that line is going to be equal to minus the activation energy over r. So when I do that, m will be minus EA over r, and the y-intercept will be the natural log of the frequency factor. And so what this will allow me to do is, if I could run the reaction at lots of different temperatures and determine the rate constant. And then if I take the natural log of all those rate constants and plot those as a function of 1 over temperature, I should get a straight line. And I can use Excel or whatever program I want to use to fit that data to a straight line. And then I can have Excel print the equation of that line on the graph, and it will give me the slope. And so then we always know r. If I know the slope, that will allow me to calculate the activation energy. And then I can use the y-intercept to calculate the frequency factor. And so this form of the Arrhenius equation is incredibly useful. All right, and so what we're showing here is basically what I've talked about in the last slide. And so here is our rearranged form of the Arrhenius equation. And so an example of one of those plots might look like is given here. So I've plotted on the y-axis the natural log of k. On the x-axis, I've plotted the inverse of the temperature. And so now I can use whatever program I want, or I can do it by hand to calculate the slope and the y-intercept of this line. And then I can set m equal to the slope minus the EA over r. I can plug in my slope, I can plug in r, and I can find the activation energy. And then I can use the y-intercept to calculate the frequency factor. All right, so I have an example here And so I have my last video on the temperature dependence of rate constants and the Arrhenius equation is actually using Excel to plot this data, fit it to a line, and then extract out the slope and the frequency factor. And I will just say, I love these types of problems. On a test or a quiz, I don't think it's practical for me to have you plot the data, but what I am very likely to do is to give you the plot and then have you calculate the activation energy and the frequency factor. So I definitely recommend watching that video because I can't stress enough how much I love these types of problems. Because rearranging an equation to write it in the form of a line is actually a really useful tool in science, and it's something that you'll probably do a lot, whatever your field is, because it is such a useful strategy.